This shows 12 hours at the famous Bay of Fundy in Nova Scotia, Canada. It's the biggest tide change in the world. But what force could move such a massive body of water?
This is a map of tidal amplitude, which is the difference between the low and the high tide in a given place. So what that means is that the low tide might be a meter below sea level, and the high tide might be a meter above sea level, and that would be a tidal amplitude of 2 meters, which is considered very high. And those high tidal amplitudes are here in red. So this is where the difference between the low tide and the high tide is the greatest. What you'll notice with this is that there are places where the tidal amplitude is very, very low. It's actually 0. And those are the places here in pink. In these places, there is no tide. Low tide is the same as high tide. What that translates to is 0 tidal amplitude. So every place in pink has 0 tide. Now, the places where there is no tide, these are called amphidromic points. I will call them tidal nodes because that's the more commoner term for them. And they're here. And these are the places, these points, that there is no tide. Literally no tide at all. And there's tons of them all over this map. There's these ones in the center of the oceans, which are quite easy to see. But if you look closely at this map of amphidromic points, tidal nodes, you'll see there's also a number of much smaller ones that operate in smaller regions. I'm going to circle these 3. Look, there's 3 tidal nodes. These are areas, again, with no tide, where the water is still all year long, all day long, all week long, no tide. Here's another one here. Here's another one here. You can see 3 in here. You can start seeing them when you look, you start seeing them all over the place here. See, there's actually 3 up here in Upper Canada. Now, the greatest density of these that I have seen is in the Polar Sea. Now, this is a polar projection map. This is a favorite by flat earthers. And you can see how many of these nodes are in the Arctic Sea. This is the Arctic Sea up here, the North Polar Sea. You can see all the nodes in here. I'm just circling them all. These are places with no tide. This is just a zoom in on that so you can see. It's almost fractal how this looks because you've got all these little nodes here and then you've also got all big nodes all in the sea. Oh, that's where the purples are. These big tidal nodes. These seem to be the center of what's going on with the tides. This is a better chart of the Polar Sea. So this is, again, a North Polar projection. I've placed a big X on the North Pole. And you can see even more in here. It seems almost like there's too many to count. Like there's areas where they're just extremely dense, these tidal nodes. So I think there's even some on these islands. These don't have to be underwater, and I'll talk about that later as well. Look at this. It seems like there's 3 in a row in here. All these tiny little tidal nodes. It's almost fractal how this seems to work. There's 2 here. This is Hudson's Bay in Canada, and I'm going to talk about that later. But first, this is the Mediterranean. There's also tidal nodes in the Mediterranean. It's not as dense, maybe, as in the Polar Sea. This is another one that's on land, actually. And I think it looks like there's one here. You can see this is Cyprus, so that's sort of how the Mediterranean here is aligned. This is the North Sea near the United Kingdom, and you can see these 2 tidal nodes here, as well as a tidal node which they've clearly marked on Sweden, or Norway. That would be in Norway. I've also got this side by side with an actual animation. Now, what's nice about this animation, it shows tides. It doesn't just show tidal amplitude. It shows tides in real time. And you can see how high these tides are relatively. These are these huge 2 or 3 meter tides that are all rushing up through this English Channel here. And yet you do have a tidal node very close into here. So you've got these massive tides, but you actually have a tidal node around here. Now this model doesn't show the tidal nodes amazing because you can see some of the tide go in through here, but it's pretty good here where you can see the tide's up on this side, then it's up on this side. It's up on this side, and then it's up on this side. And the tidal node itself, the sea level never changes. So this is a better map, a more detailed map of the tidal nodes, and it shows another tidal node with this arrow around New Zealand. So New Zealand's another example of a tidal node that's not under the ocean but still seems to affect the tides. And what I mean by affect the tides is you can see this arrow, tides revolve around tidal nodes. So a high tide seems to be a bulge of water that will revolve in a certain direction, and it looks like the direction is different in these different nodes. There's clockwise and there's anti-clockwise, but it has nothing to do with the equator, because this one you can see here is clockwise. This one you can see is counterclockwise. This one you can see is also clockwise, and this one here is counterclockwise, and there's really no pattern to whether it's going to be clockwise or counterclockwise. This shows a live animation of the tides, and you can see exactly what I mean when I say that tides revolve around the nodes. So I told you about those two nodes up here in Hudson's Bay. You can see the high tide in red revolving around the coast of Hudson's Bay. You can also see this in New Zealand, which I told you was an on-land tidal node. You can see this high tide in red spinning around New Zealand, and the low tide in blue, some negative tide, also spinning around New Zealand, and they almost look like magnetic fields in the way that this is pictured here around New Zealand. So this is Hudson's Bay again. This is a different tidal animation, and you can see how these tides seem to revolve around Hudson's Bay. And again, there are tidal nodes, two tidal nodes here in the center of Hudson's Bay that show no tidal movement whatsoever, while you have huge tidal movement around these shores. And this, again, is New Zealand, and this shows those tides revolving around New Zealand. This is a very helpful map. It is a globe model, but it's a helpful map. This shows you the relative, how relatively really very high these tides are in some of these areas. Now, this only shows half the Earth. You can see a little bit over here in North America. But if you look at South America, the tides are just enormous at the very, very tip of South America. The same is true up here in Great Britain and in the English Channel. Huge amount of tides. If we go back to this earlier map, you can see that there are all those tidal nodes there at the base of South America, just like you may expect if these tidal nodes were what's creating these tides, because you've got a high density of these tides, so you're actually moving a great deal of water against this continent of South America, which is why you've got this black here. This is, I don't know how tall the tidal amplitude is right here, but it's very, very high. I think in some places the amplitude is as much as 4 meters. So this could be a full 4 meters here at in Argentina down here. This is from the Wikipedia article on tidal nodes, and it's extremely sparse. There's very, very little information about what these are and what they do. There's a line about how the moon causes them, but it's frankly laughable that people can think, after looking at tidal nodes and how tides react around tidal nodes, that the moon is doing this. You've got this joke of an animation here on the bottom right that does not correspond whatsoever with the models I've shown you, as well as this one on the top where you have a bulge both on the moon side and on the non-moon side, and nothing on the top or bottom, even though we know that there's a great deal of tide in the southern part and in the northern part of what would be this map here. There's also a list of tidal nodes on Wikipedia. The set of clockwise, points include these, but they've only given us 16 nodes here, but from what I saw from the map, there's 100 of these things. It could be 100. I haven't even counted them. There's so many of these tidal nodes all over the Earth, but in some places they are in far greater density than in other places. what got me into looking at this was taking a trip to Hawaii. I'm from Vancouver. This is a picture on the right of a Vancouver tide. And I went to Hawaii expecting tides to behave similarly as they would in Vancouver. I think most people just assume tides are the same everywhere. But the difference between low tide places and high tide places is it could be a matter of 12 feet, which is, a tall man twice. It's actually an enormous amount of water we're talking about. So it wasn't going on in Hawaii. Hawaii has lots of waves, which I don't think are related to tides. They seem to be wind related in a lot of cases. But the tides, I didn't notice at all. You always notice tides in Vancouver, but I never noticed it once in Hawaii. So I looked into it. I have a few speculations about what tidal nodes are. They could be a sea life living deep under the water that's affecting the water, the movement of the water somehow. I've put in the background my favorite sea life, which is the kraken. It's also it's a fantasy sea life because it's so giant. Nothing that giant exists that we know of. Or plate boundaries. It could just be where tectonic plates collide and where they're moving against each other. The same thing that causes volcanoes, seems to cause volcanoes and earthquakes, could also be causing the tides. And the third speculation is not my speculation, but it's the speculation that everybody accepts, and that's that the moon is causing the tides. And for everybody, for this to be the consensus, the scientific consensus, is extremely embarrassing. It is extremely embarrassing to me that this is the best that science can give us. And this is a model of what the tides would look like if it was the moon. And this is on YouTube as, in fact, what the tides do. But this is nothing like what I've shown you in this presentation. This is pure fantasy.